Hello and welcome. Today we're doing a question from LeetCode called Path Sum 3. This is from LeetCode 75. It's a playlist we've been doing. And of course I have that playlist linked down below if you do want to check it out. So what are we being asked? Given the root of a binary tree and an integer target sum, return the number of paths where the sum of the values along the path equals target sum. The path does not need to start or end at the root or a leaf, but it must go downwards, traveling only from parent nodes to child nodes. Example 1, this is our binary tree over here, and we need to find a target sum of 8. So all the paths that will sum up to 8. We have 3 of them, 5, 3, 5, 2, 1, and -3 and 11. And if you notice, we can't go across any node. We can't go up and then back down. We can only travel in one direction. That's from parent to child. And example 2, we have the following tree over here, and our target sum is 22. So to visualize this a little bit better, let's take a closer look at it. So I have example 2 down below. We have 5, 4, 8. Then we have 11, null, 13, 4, 7, 2, null, null, 5, and 1. And of course, target sum is 22. Now, before figuring out all the paths that will actually give us the sum of 22, let's think about how to actually get every single path sum. We know initially we could get a path sum of 0 by taking no node within our tree. So we can get a total sum of 0 by taking no node. Then if we take the node of 5, we would get a total path sum of 5. If we wanted to go left, bringing 4 into the mix, our total with 5 and 4 would be 9. And if we didn't want to include this 5, another possible path we could make is just 4 by itself. So we could also just have 4 by using node 4. So up until this point, with only 5 and 4, if this was our tree at this point, these are all the possible path sums we could have, 0, 5, 9, and 4. Bringing 11 into the mix, what are all the possible path sums we can make at this point? Well, adding 11 to 9, right, just adding that on to the end of this, we would get a total of 20. 11 plus 9 is 20. So to get 20, we would go 5, 4, and 11. This is one possible path sum with 11. Now, what if we didn't want to include 5? We just wanted this segment of our path sum. Well, we could remove 5 from 20 to get us a total of 15. And that would be through these two nodes over here, 4 and 11. And if we wanted an even shorter path, the only other possibility is to remove both of these. So removing 9 from 20, we would get 11, our own node. So another path sum would be 11. Now continuing this, say we go down further to 7, we would add 7 to 20. So right now, this entire path would give us a total of 27. So 27 would be 5 plus 4 plus 11 plus 7. So 27 is going to be that entire path sum from the root node to our own current node. Now we want to figure out all the path sums we can get with this new node that we brought in 7. So we want to find all the paths that end at our node. We have one from the root to our own node. Now we want one from the second node to our node. So we just want to remove 5 from 27. So we'll get 22, and that's going to be from 4 plus 11 plus 7. Then removing 9 from 27, we basically remove both of these. We would get 27 minus 9, we'd get 18. And the path sum of 18 is going to be acquired from 11 plus 7. And we can also remove 20 from 27. We know 20 was 5 plus 4 plus 11. That entire path sum from the root node to the node just before us. So if we remove that entire segment, we'll just be left with our own node. So we can also get a total sum of 7 using our own node. So at this point, we found all the possible path sums we can get from 5 to 7. Everything within this path we found. And if you notice, right, we don't actually need to calculate everything individually. All we need to do is keep track of the current path sums for every single node from the root to that node. What do I mean by this? For 5, we just need to figure out the path sum from the root node to 5. So that's 5. Then for 4, we want to do the same thing. From the root node to 4, what is our path sum? That's 5 plus 4, which is 9. And we can figure out all the path sums we can make up until this point just by subtracting. We know we can remove 5 from 9 and get all the other path segments that we want that end at 4. And doing the same thing at 11, right? We figured out our entire path sum by just adding 11 to 9. We got 20. Then from 20, we just need to subtract 5 and 9. So if we remove 5, we're left with 4 and 11. Then if we remove 9, we get rid of 4 and 5 entirely. We get 11 by itself. And same thing for 7, right? We add 7 to this current total that we had. We went to 27. And if we want to figure out all the sums we can get that end at 7, we can do that by using our previously calculated path sums from the root node to that current node. We'll just subtract 5 from 27 to get 4, 11, 7, this path over here. Then we'll subtract 9. We're getting rid of 5 and 4, this segment entirely. So we'll be left with this path over here. Then we can get rid of 20. So we're getting rid of everything from 11 to 5 to just be left with our own root node as our path. And that's all we need to do. So at this point 7, we figured out all of our possible sums. We saw we were able to get 22 with one of them. So now we're going to go back up to 11 and go down all the other paths. So we just finished 27. And now we want to go down here. So we're back at this sum of 25 plus 4 plus 11. And we're going to add 2 to that sum. So we get to 22, and we get to 22 by doing 5 plus 4 plus 11, just adding our own roots value to the end of that. And say I'm looking for a very specific target sum, right? I'm looking for a path sum that will sum up to 13, for example. What I can do is take my current sum, so my current sum, which is 22, and from that, subtract the target sum that I'm looking for. So from here, I'm going to subtract target sum, which is 13. So 22 minus 13. What does that equal? 22 minus 13 is 9. And all I need to do is see if 9 exists in all my previously calculated path sums from root to that current node. And it does, right? We see 9 over here. What that means is we can remove a segment of 9 and get the sum we're looking for. If I remove 9, which was 5 plus 4 from here, and I know my current total path sum from 5, 4, 11, 2 is 22, then I can find a path sum of 13 that I am looking for. It's going to be 11 and 2. So what I'm going to do every single time at the node I'm on is find my current sum from the root node to my own node, then subtract the target sum to see if there is a segment that we can remove to give us that path we're looking for. And that's it, really. So we know this is a binary tree and we're going down a path, so we want to solve this using recursion and a DFS. We also know we want to figure out all of the path sums we have from a node to a given node and keep track of that. So we're also going to have a dictionary storing that, as well as a running current sum. We'll keep track of the current sum we have in a certain path, and as we go down nodes, we'll just add our own node's value to that path. And every single time, we're just going to subtract our current sum minus the target sum, see if it already exists. If it does, we know we can get to a path sum that sums to the target sum we're looking for. So now that we know what to do, let's go ahead and code this up, and then we'll do a complete walkthrough to make sure we truly understand exactly what's happening. Okay, to code this up, we know we want to return the number of paths that sum up to our target sum. So we're going to initialize that. Solve.paths is going to be 0. And we also want a dictionary keeping track of all the path sums we've seen so far. So solve.pathSums is going to be a default dictionary of integers. So let's import that as well from collections or default dict. And we know initially we are going to have a path sum of 0 with no node. So there's going to be one way to get to the path sum of 0. So solve.pathSums of 0 is going to equal 1. We want to store the number of ways we can get to a certain path sum. Because say in this example over here, we had a sum of 22 from 5 to 2. And say there were actually 2 ways within this path, say there was an extra node 0 over here, to get to 9. That means there would have been 2 segments of 9 we could have removed. And so there would have been 2 different paths that would have gotten us 13, which is why we want to store the number of ways we can get to a certain path sum. Once all these initializations are done, we can go ahead and write out our DFS function. Now, for the DFS function, I prefer writing it within this bigger function over here, just less variables we need to pass in. So defining it within this function, let's call this DFS. We know it's going to take in a node, so let's call that R, and a current sum that we've been building. We're going to be passing in a current sum from the root node to our node and keep building as we go down. So let's also pass in current sum. Now with a recursive function, there are 2 things we need to keep in mind, our base case and our recursive case. For our base case, when do we stop recursing? If R is none, we're going to stop. So if R is none, we simply return. If that's not the case, we want to update our current sum with our own value. So it's going to be current sum plus equals r.val. We're updating our current sum as we go down nodes. Now we also want to see if there are paths that we can actually make that sum up to target sum. And we know how to do that, right? We just need to check for current sum minus target sum and see if there's any segment we can remove from our dictionary. So we're going to do current sum minus target sum. and check this in path sum. So solve.path sums of current sum minus target sum. However many ways we can remove that segment are the number of ways we can make a path that sums up to our target sum. So we're just going to add this to solve.path. Solve.paths plus equals solve.path sums of current sum minus target sum. Once that's done, we're going to add our own updated value of current sum to the dictionary. So solve.path sums of current sum plus equals 1. There's one more way to get to our current sum. It's going to be from the root node to our current node. Now, all we need to do is do the same thing for our right and left children. So if r.right, if there is a right child, we're just going to call DFS again with r.right and our updated current sum. So current sum. And we're going to do the same thing for the left. So if r.left, we're going to call DFS with r.left and current sum. Now, once that's done, once we've gone down to our child nodes, we no longer need to keep track of our path from the root node to our current node. The only reason we're keeping track of it is if it could be a potential segment to remove for a future path down the line. If that's no longer the case, we're not going down our nodes anymore. We don't want to keep track of it, and we're going to remove it from our dictionary in order to avoid any duplicate countings. So solve.path sums of current sum is going to be minus equals 1. And that's it for our DFS function. We just want to go ahead and call this. So we're going to call DFS with root and current sum of 0. And in the end, we just want to return solve.path. So we're going to return solve.paths, which is going to store the number of paths that sum up to target sum. So let's go ahead and submit this. And it is accepted. Now, talking about space and time complexity, for time, we are going through every single node. So that's going to be O of n. And for space, we are storing in a dictionary all of our current sums, which could be unique for every single node that we go on. So it's also going to be O of n for space. Now, before leaving, we're going to do a super quick walkthrough with an example so we can see exactly how our code is going to run line by line. Today, for our input example, we have the following tree and our target sum is 1. Going through our code line by line, the first thing we do is all of our initialization. So solve.paths is 0. Path sums is a dictionary, and it's going to have 0 as a key with a value of 1. There is one way to get a path sum of 0, and that's by taking no nodes at all. So solve.paths is 0. This is our dictionary, and it's going to be one way to get to a path sum total of 0. We define our DFS function over here, and now we're going to call it with our root node of 0 and our current sum, which is going to be 0. So we're passing in 0 for r and 0 for current sum. R is not none, so we don't return. To our current sum, we're going to add our own root's value from the root total path sum that we have. So adding 0 to 0, it's going to keep it 0. And solve.paths plus equals solve.path sum from current sum minus target sum. Our current sum has been updated. It's still going to be 0. So current sum is still 0 over here. Now we want to see if 0 minus target sum. If 0 minus 1, so -1, exists in our dictionary. Is there a path from the root node that equals -1 we can just remove to get a total sum of 1 that we're looking for? There doesn't, right? We only have 0 in our dictionary, so we can't add any more ways to get to a path sum of 1. And instead, we're just going to update path sum to say that there's one more way to get to the current sum of 0. 0 is already in there, so now there are going to be 2 ways to get to 0. Either we take no nodes, or we take our own root node. Now that that's done, we're going in here, if r.right, that's not true, right does not exist, so now we're checking the left child. So if r.left, that is true, we're going to call DFS again with the left child of 2. So we're calling DFS again with r being 2 and current sum being 0. R is not none, we don't return. To current sum, we're adding our own node's value. So this is the node that we're on, and our current path sum from the root node to our current node has a sum of 2. Now we want to check here, right? Current sum, which is 2, minus target sum, which is 1. Does there exist a path from the root node to some node in the middle of root and our node that has a sum of 1? It doesn't, right? We've only seen 0, so we can't update self.paths, and instead we're going to update path sums. So there's one more way to get to a path sum of 2. And now we check if r.right, that is true, there is a right child, so we're going to go down in here. So now we want to call DFS with r.right, which is going to be 3. And current sum, which we had updated to be 2. We go back in this function, our new r node is this over here. It's not none, so we don't return. we're going to update current sum. So now current sum is going to be 5. We had a current sum of 2, and to that, we're just adding our own node's value, which puts us at 5. Now we want to check 5 minus target sum of 1. Does 4 exist somewhere in this path? It doesn't. We don't see it in this dictionary. Instead, what we're going to do is just update path sum. So there's one more way from the root to a node to get a path sum of 5, and that's from 0 to 3. If r.right, this is true, we're making that same call again. Now we're calling DFS with r being -2 and current sum being 5. It's not none, so we don't return. We're updating current sum to add our own value, -2. So 5 plus -2 is 3. And we're making a check. Current sum, which is 3, minus target sum, which is 1. Is there a way to get to 2? We go into and we see there is one way to get to 2. There is one segment that we can remove to get us to the sum of 2. So there's going to be one way to get to the path with the target sum of 1. So we're going to update self.paths with 1 over here. And intuitively what this means, right? We're in this path over here from 0 to 3 to -2. We have our path sum from root node to our current node equaling 3. There is a segment we can remove, 0 to 2. So we're left with a path that does equal to our target sum of 1, 3 and -2. This path right here equals what we're looking for, which is 1. So there's one more way to get to the path that we want. Now that that's done, we're going to add our own current sum path to path sums. So there is one more way to get to 3. And the reason we want to keep track of this, right? Say we had child nodes and the current path sum for one of our child nodes from the root node to that child node equaled 4. We would have overshot what we are looking for by 3. We can remove this path of 3 to give us that target sum we want of 1. But since there is no right, we don't go in this condition. And if there's no left, we don't go in any condition here either. There's no child nodes for -2. So instead, we're just going to remove this, right? This is not useful anymore. We're not going in any child nodes. So there's going to be one less way to get to 3. We're just removing this entirely. Now that this is done, we've returned out of this function. We can return back to our caller. So we go to our caller, the node of 3. We had just finished going in the if r.right condition. Now there's nothing to the left of us. There's no left child. So we can't go in this if condition. And all we're going to do is subtract 1 from the current sum we added to path sums. Our current sum was 5. So we're going to subtract 1 from that, which puts 0 as the value for key 5. And now we can return up back to our caller. So we're going to go back. We're at node 2 and we had just finished going into the right. Now we check if r.left. That's true. So we're going to go into this condition over here, making another DFS call. So we're in DFS. Our node is now -1. The current sum was 2 that we're passing in. 2 current sum we're updating with our own value. So our new current sum is going to be 1. And we want to make a check. Current sum, which is 1, minus target sum, which is also 1, is 0. How many ways can we get to 0? There are 2 ways. So now there are 2 more paths to get to 1, which puts our total at 3. Now, what does this mean, right? We have a total of 1 once we get to here, but we can remove 0 2 ways. So there are 2 paths that get us to that total sum we want. One path is from the root node to -1. This is a sum of 1, 0 to -1. Another way is to remove this root node and just use 2 and -1. This is also a sum that gets us 1. So that's why there are 2 ways to get to that target sum, right? Now we're going to update path sums. There is one more way to get to a total of 1. That's from 0 to -1. We check if r.right, that is true. So now we are on node 0. We're calling this with r being 0, current sum being 1. Root node is not none, we don't return. We update current sum with our own values. So our current sum is going to stay 1. To our current sum, we're adding 0, so it stays 1. Now we make a check. Current sum, which is 1, minus target sum, which is 1, 0. Is there a way to get to 0? We know there are 2 ways, so there are going to be another 2 paths to get to our target sum, which means there are going to now be 5 paths in total. And again, why is that? We can remove 0 in 2 ways. One way is to remove no node. So we're going to go from 0 to 2 to -1 to 0. The sum of this is going to be 1. Another way is to remove our root node. So we're going to have 2, -1, and 0. This here is also a path that sums up to 1. So we have 2 more paths that sum up to 1 with the addition of this node. Now we're going to update our current sum. There's one more way to get to that sum of 1. So now there are 2 ways to sum up to 1. And if r.right, there is no right child, we don't go in here. If r.left, no left child, we don't go in here. We're just going to subtract from path sums our current sum of 1. So now there's going to be one less way because we're returning back to our caller. Returning back to our caller, -1. We just came from the right. We check if r.left, that's not true. We don't go in here. So we're going to remove 1 from the current sum that we have so far. Our current sum was 1, so now there's one less way to get to 1. So it's going to go to 0, and we're going to return to our caller. Now, our caller had just gone to the left in this condition. We're out of this condition, and we're now going to remove 2 from our dictionary. So there's one less way to get to 2. Going back, returning to our caller. At this point, we were in our original call. So we just gone in the left over here, and now there's also one less way to get to 0. So we're going to subtract from our dictionary. And this is that original one we had from here. So this is okay to, and we're going to return to our caller, which was this call over here. There's nothing else to do now except return solve.paths, which is going to show exactly how many paths sum up to 1. And it's going to be 5. So we just went ahead and solved path sum 3 from LeetCode with an example. If you have any questions though whatsoever, of course, let me know down below. I will answer all of them. If this video was helpful, like, comment, share, and subscribe. It really supports the channel. And as always, I will see you in the next one.